the beam carry central point load as shown in the figure. So we have considered simply supported beam of span length L, and concentrated or point load is acting at the center, and that central point is C. Now first we have to make the shear force diagram calculations. The conventions which we have used for shear force diagram calculations are: the upward force is considered as positive and this downward force is considered as negative. So these are the conventions which we have used for run the shear force and shear force diagram over here. Now as we know that we can find out these reactions RA and RB. These are known as the support reactions. Now as the load is acting at the center, half of this particular load will be shared by this left hand side reaction, and half of this particular load, that is W by 2, will be shared by the right hand side reaction, that is RB, and hence RA and RB both are same, that is W by 2 in this particular case. Now this RA and RB we can easily calculate by applying the conditions of equilibrium also. Now we'll start with the shear force diagram calculations. So shear force at point A is nothing but reaction RA, which is acting in the upward direction and hence positive. Shear force just at the left of C without considering this point load will be same as that of A, because there is no other force that is acting between A and just at the left of C. So whatever is the shear force at A, the same will be written over here, that is W by 2. But exactly at this point C, there is a point load or concentrated load of W which is acting in the downward direction. And hence to this W by 2 will have to add in the negative direction this point load, that is W, and therefore shear force at point C will be minus W by 2. Now shear force at B left, just at the left of B, again there is no load or force that is acting between C and just B left. We can say that whatever is the shear force at C, the same will be acting at B left also. But exactly at B, there is an upward acting reaction or point load of W by 2. So this minus W by 2 and plus this W by 2, that is RB. And so we can say that shear force at point B will be 0. So all these shear forces we have shown over here on this shear force diagram. So this is the baseline that we have drawn over here. Now shear force at A is W by 2, shear force at C left is W by 2, exactly at C it is minus W by 2, again B left it is minus W by 2, and at B it is 0. So that will complete our shear force diagram. Above the baseline the diagram is positive, below the baseline the negative values we have taken. So actually there is no need of writing down these negative values over here, because this diagram is in the negative, these values they are in the negative region or below the baseline. Now we'll consider the bending moment diagram calculations for the same beam. Now we know that as in case of the simply supported beam, at the end points, that is at these particular points A and B, the bending moment is always 0, because there is no force that is acting on the left hand side of A. Similarly, there is no force that is acting on the right hand side of B. So we can say that bending moment at A is 0 and bending moment at B is also 0. Now we have to calculate the bending moment at point C. Consider all the forces which are acting on the left hand side of C. Now there is only one force that is acting on the left hand side of A, that is RA, and its magnitude is nothing but W upon 2, and it will produce a clockwise moment as shown by this arrow, and clockwise moments they are considered as positive. So from A to C the perpendicular distance is L by 2. So bending moment at C is nothing but RA multiplied by this L by 2 distance. Substitute the value of RA. RA is nothing but W by 2. So it is W by 2 into L by 2. So answer is WL by 4. Using these values, we can draw now the bending moment diagram. First, draw this baseline. So at the end points, bending moment is 0, and at central point C, bending moment is WL by 4, as we have already calculated. And this will complete our bending moment diagram. Now we'll consider the second case in which the load is eccentric. It is not acting at the center. In the previous case, it was acting at the center. So suppose this load W is acting at a distance of A from the left hand support and at a distance of B from the right hand support. The reactions Ra and Rb are given in this particular case as Wb by L and Wa by L, and these reactions which we can easily calculate by applying the conditions of equilibrium. The total span length is L, so L is equal to A plus B. Now first we'll draw the baseline. Start with the shear force at A. Shear force at A is Wb by L because reaction at A is Wb by L. Just at C left, there is no other force that is acting between A and C. Whatever is the shear force at A, the same will be acting at the C left. So this same value we have written over here also. Then shear force at exactly at point C. To this particular load, that is C left load, there is a point load that we will have to add in the negative direction. So it is Wb by L minus W. Take W common, so it is B upon L minus 1. So it is B minus L divided by L. Take the minus sign common, so it is minus W into L minus B upon L. But as you know that L is equal to A plus B. So L minus B is nothing but A. So we can say that for this L minus B, we can substitute. So this L minus B is nothing but what? It is A. So it is minus WA by L. Now shear force just at the left of the B, as there is no force acting between C and B left, we can say that the same load will be acting at B left also. So minus WA by L, the same load will be acting at the B left also. And now exactly at point there is an upward acting force of WA by L, and that is positive. So this minus WA by L as it is plus WA by L, so that value is 0. So we can say that shear force at B is what it is. So let us draw the shear force diagram. All the values which we have calculated, they will be shown over here. So Wb by L is the shear force at A. Shear force at C left is also Wb by L. Shear force exactly at C is minus Wa by L. B left it is minus Wa by L, and at B it is 0. Now for the same arrangement, we have to draw the bending moment diagram. So bending moment diagram calculation, the conventions are clockwise positive and anti-clockwise negative. So bending moment at A and B, it is 0, as we have seen already. Similarly, to calculate the bending moment at C, consider all the forces which are acting on the left hand side of A. Consider all the forces which are acting on the left hand side of C. So on the left hand side of C, there is only one force that is acting, that is Ra, and it is producing a clockwise moment, and clockwise moments they are considered as positive. So Ra multiplied by perpendicular distance. So perpendicular distance from A to point C is small a. So it is Ra into A. Substitute the value of Ra. Ra is Wb by L into small a. So it is Wab by L. So these values they are plotted on the diagram. We get this bending moment diagram in this particular case. Now let us see another case in which we are having a simply supported beam carrying u.d.l of W Newton per meter over the entire span length. We have considered the section XX also acting at a distance of x from the left hand support. Now we know that in case of the concept of the uniformly distributed load, it is nothing but the load which is acting for 1 meter length. So W Newton per meter, the meaning of this is that for 1 meter length, it is the load that is acting is W Newton. Now in this our case, the total length of the span or the total span length is L, and therefore the total u.d.l length will be W into L, and half of that will be shared by left hand reaction, and half of the WL will be shared by the right hand side reaction, and hence Ra is equal to WL by 2 and Rb is equal to WL by 2. Now let us start with the shear force diagram calculations, assuming the same convention, that is upward force positive and downward force is negative. Now first we'll form one general equation in terms of x. So, and for that purpose only we have to consider the section xx acting at a distance of x, as we have already seen. Now consider all the forces which are acting on the left hand side of this section. So on the left hand side of section xx, the force, upward force that is acting is Ra, which is WL by 2, that we have written over here, and the u.d.l of W multiplied by x, because x is the length between A and this section xx under consideration. So W into x, that is the downward acting load, and therefore it is negative. Now we know that the distance x is measured from point A, and therefore at point A the value of x will be 0, and therefore in this equation, general equation that we have formed, in place of x substitute 0, so that you will get shear force at A is equal to WL by 2. Now at point C, the value of x is nothing but what? It is L by 2, because C is the center point of this beam. So in place of x, again substitute L by 2, so it is WL by 2 minus WL by 2. So value of shear force at C will be 0. Now at point B, the value of x will be L, because it is the total span length that we have to consider. Again x is measured from A to B, and therefore from A, and therefore A to B length will be L. So x is equal to L, we can substitute. So in place of x substitute L. So it is WL by 2 minus WL. So it is nothing but WL minus 2WL upon 2. That is minus WL by 2. So that is the shear force at B left. And exactly at point B, there is suddenly a point load of WL by 2 acting in the upward direction. So in this particular load, we have to add this upward acting load of WL by 2. So minus WL by 2 plus WL by 2. So total load will be 0. So all these values we have used to draw the shear force diagram. So at A is WL by 2, at C is 0, at B left is minus WL by 2, and at B is 0. Now let us try to understand how to draw the bending moment diagram in this particular case. Again consider the section xx at a distance x. The u.d.l load for this section is W into x, because W is for 1 meter, then for x meter the load that is acting is W into x. Now for the calculation of the bending moment, we will convert this u.d.l load into point. So this W multiplied by x is the u.d.l load, and allow it to act at the center of this length, that is from this to this, whatever the length is there, that is nothing but x. It will be acting at a distance of x by 2. So we have converted this u.d.l into point 2 for the calculation of the bending moment. Now I'll take moment about this section xx. So first we are finding out bending moment about section xx using the conventions, that is clockwise is positive and anti-clockwise is negative. Now start with Ra. Ra will produce clockwise moment. So Ra from A to this section, the perpendicular distance is x, so Ra into x, and it is producing clockwise moment, and hence it is positive. Then this u.d.l, which we have converted into point load, will produce anti-clockwise moment about this section xx. So it is minus, the u.d.l load is wx and perpendicular distance is x by 2. So it is minus wx into x by 2. Substitute the value of Ra, that is WL by 2. Now again we will find out bending moment at point A, and we know that at point A x is 0. So if you substitute x is equal to 0 in this equation, so this is our governing equation, and in this equation we have to substitute the various values. So at A x is 0, so in place of x substitute 0, in place of x it is 0, in place of this x also it is 0. So we can say that bending moment at A is 0. Bending moment at point C, which is the midpoint or central point of the beam, x is equal to L by 2. So in place of x we have to substitute L by 2. Again here also L by 2, and here also in place of x it is L by 2. So we can say that it is WL square by 4 minus WL square by 8. That is nothing but WL square by 8. Finally, bending moment at point B we have to find out. We know that at point B the total length, that is x, is equal to L. So again in this formula, in place of x we can substitute L, In place of x, it is L, and in place of this x, it is L. So it is WL square by 2 minus WL square by 2. So answer will be what? It is 0. So we can say that bending moment at point B is 0. Now, as it is a second order equation, W square by 2, so it is a parabolic curve as shown over here, and at any points the bending moment is 0. So in this way, we can draw the bending moment diagram in case of simply supported beam carrying uniformly distributed load of W Newton per meter over the entire span length. Thank you very much for watching.